Today we study oscillations. In the first semester, you have studied the oscillations in detail already, but in the circuit analysis, especially for RLC circuit, its classical mechanics analog is the damped harmonic oscillator that we have already studied. But to go ahead with the RLC circuit, it's better to review the classical mechanics problem for that corresponds to RLC circuit, that is the damped harmonic oscillator once again. Okay. We review fundamental concepts of uniform circular motion first. Uniform circular motion is uniform circular motion. This is a uniform circular motion. The angular speed is constant on the plane. The motion along a circular orbit with the constant angular speed is called the uniform circular motion. And the projection of a uniform circular motion along either x or y axis satisfies the simple harmonic oscillation. Mechanically, simple harmonic oscillation corresponds to the equation of motion for a massive object that is connected to a spring without frictional force. Once the frictional force, the damping force, is applied, the system is a little bit more complicated than the simple harmonic motion, and it becomes the damped harmonic oscillation. That are inevitable in our analysis involving circuit equation for RLC circuit. We first review the uniform circular motion. In two dimensions on the xy plane, the position vector of a point on a circle of radius r. Radius r, this is a circle, center is at the origin, can be parameterized by r equals overall vector r is the length of the radius, I hat cosine theta, and j hat sine theta is the unit radial vector. We know the unit radial vector r hat is I hat cosine theta or j hat sine theta. It is a unit because r squared equals cosine squared theta plus sine squared theta is always 1. So this is a unit vector, and the direction is I have theta, x component is cosine, y component is sine, so this is a radial direction. The theta is the angle. The polar angle theta rotates from the x-axis counterclockwise. Suppose that the angle is a function of time. This theta, polar angle theta, is proportional to time, and omega is a constant. Then its angular frequency becomes constant. We take the time derivative theta dot, that is d theta over dt equals omega, because the omega is constant as t is linear. We say this particle is making a uniform circular motion. The chain rule of the differentiation can be employed to evaluate the following derivatives. Cosine theta is actually omega t, So if I take the derivative with respect to time, we take the derivative of cosine theta with respect to theta, and this one is a minus sine theta. And then we take the derivative of theta with respect to t, then theta dot is omega. Therefore, this value is minus omega sine theta. In a similar manner, we can take the derivative of sine theta with respect to time. Then we first take the derivative with respect to theta, and we take the time derivative of theta. This is a chain rule. The derivative of sine theta is cosine theta. Hence, time derivative of sine theta is omega cosine theta. We defined unit vectors along the radial and tangential directions. We have already confirmed that r hat is a unit radial vector. Unit vector along the angle theta is perpendicular to the unit radial vector. So cosine, sine, and sine, cosine with flipped sign in front of the x component. Then we take the scalar product, theta squared is minus sine theta squared plus cosine squared. So it is 1. So this is a unit vector, and r dot theta hat equals I dot I minus cosine theta sine theta plus j dot j sine theta cosine theta. So these two contributions cancel, so it is 0. That means r hat and theta hat are orthogonal. The x component is negative and y component is positive. So the direction is in this direction. That is toward the increasing direction of the polar angle. So unit radial vector and unit vector along the angle, polar angle. Let's see. This vector is depending on angle. For example, r changes depending on angle, and theta changes depending on angle. Okay, so why don't we take the derivative? However, I hat, j hat, I hat, j hat. These are unit vectors fixed to the Cartesian coordinates, and these are constant vector. Thus, if I take the time, the derivative with respect to angle, r hat has a derivative with cosine theta. Derivative of cosine theta is minus sine theta. Derivative of sine theta is cosine theta. We find that this one is identical to theta hat. And then theta hat, we take the derivative. Theta hat is this one, and derivative of sine theta is cosine theta, and derivative of cosine theta is minus sine theta. We find this is minus 1 is a factor equals to minus I hat cosine theta j hat sine theta. Hence, this is the unit radial vector. unit radial vector. Therefore, this value is opposite unit vector relative to the unit radial vector. As we already have evaluated, square of unit radial vector r hat and square of the unit tangential vector is also 1. That they are unit vectors, and r hat, beta hat, their scalar product is vanishing. Thus r hat and beta hat are orthogonal to each other. In summary, beta hat is making a right angle with respect to the radial vector. Thus, this tangent vector beta hat is tangent to the circle at a point on the circle. The unit radial vector is normal to the circle at a point on the circle. Unit radial vector is normal to the tangent. In summary, we find the first order time derivative. First, radius itself is constant. Radius r equals constant. But unit radial vector changes with respect to the angle. So applying chain rule, we compute this, and previously we have obtained this one at theta hat, and it was minus r hat, right? And time derivative of angle, the theta dot, and that is omega, and this one is the same as this. As a result, time derivative of unit radial vector is omega times tangent vector. Time derivative of tangent vector is minus omega unit radial vector. Here we have assumed that uniform circular motion, thus omega, is independent of time. If I take another time derivative to find the second order time derivative, what we do is omega is constant, so omega dot will vanish eventually. So this is useful in general. However, in our uniform circular motion, this contribution vanishes. Instead, we have the only non-vanishing contribution in here. Now this omega is here, and the time derivative theta dot is minus time derivative of theta dot here, minus omega r. Here we have already negative sign on it, minus omega, and time derivative of unit radial vector, that is theta hat. In both cases, whether it is a radial vector or tangent radial vector or tangent vector, second order time derivative of itself, except that there is an over factor minus omega squared. Alright. And actually, double time derivative of position vector is double time derivative of radius and unit radial vector, and this is constant, so r is vectored out. Double time derivative of unit radial vector The result is this one. This one, substitute. Because r vector is r unit vector, this is minus omega squared r, and double time derivative of radius. Finally, move this one. That means plus omega squared r equals 0 vector. This is the equation of motion for the uniform circular motion. Now, double time derivative of displacement, this is acceleration, okay? And this is minus r vector omega squared. Number 2, the position, velocity, acceleration of a particle under uniform circular motion. In summary, position, velocity, and acceleration obtained like that. You also need to understand period. Omega is a constant. Omega t, when omega t reaches the period of an angle, there's a phase, then we say this one is a period. So period t equals 2 pi over omega, or omega is like that. So average speed is our omega. That can be evaluated. The circumference is 2 pi r, period r. So distance divided by time, this is average speed. And actually instantaneous speed is the same as this. The relation leads to this kind of relation. Acceleration is minus v squared over r. And negative sign means the force is toward the center of the orbit. If there is no force, then particle wants to make a straight, go straight due to the Newton's law of inertia. However, because of the centripetal force toward the center, it makes a circular motion. Next, we consider simple harmonic motion. Frequency f is defined by 1 over period. For the oscillatory motion is the number of oscillations per second. In SI unit system, it is measured in hertz. Hertz is inverse reciprocal of second. The period t is the time required for one complete oscillation or cycle. The cycle is called one complete oscillation. It is related to the frequency reciprocal. Simple harmonic motion. In simple harmonic motion, the displacement of a particle from its equilibrium position is described by the equation. And as we have already found for the uniform circular motion satisfies this equation, the simple harmonic oscillation, we should find that the solution is the projection onto onto a Cartesian coordinate, either x direction or y direction. For example, R is I hat x plus j hat y. Therefore, each component satisfies the same equation. The solution to this simple harmonic oscillator is this one. We have frequency, characteristic frequency, phase constant, and amplitude. So oscillation from relative to the equilibrium position it oscillates with amplitude xm. So maximum value with respect to this origin is plus xm and minimum value is minus xm. You find either cosine or sine can be the solution of this. So omega t plus pi is phase, and phi is a phase constant. The angular frequency omega is related to the period and frequency of the motion. In fact, the simple harmonic oscillator equation of motion is F equals ma. M x double dot is force, restoring force kx. It's x double dot plus k over mx equals 0. We find this is x double dot plus omega squared x equals 0, and omega equals the square root to k over m. Next, we consider linear differential equation. Homogeneous linear differential equation. Homogeneous means the right-hand side is equals to 0, homogeneous. If it is not equal to 0, then done. We call it non-homogeneous equation. Differential equation is an equation for some function of x, and the left-hand side is a linear combination of a function and its derivatives, first order, second order, and so on. But in physics, in equation of motion, acceleration is the double time derivative, and velocity is a single time derivative of the displacement. So we are mostly interested in the second order linear differential equation. It is called linear because they are linear combinations of the function, first order derivative, and second order derivative and multiplied by some numbers and add it up together. So this is a linear differential operator. In this class, we are mostly interested in the case A, B, and C are all constants. First, we consider the superposition principle. When we consider the homogeneous differential equation, if x1 and x2 are the solutions, then the linear combination of these two is also a solution. For example, Lx1 t equals 0. We multiply some constant c1, and this constant is after taking the derivative, it vanishes. So this is c1x1 equals 0, 2. In a similar manner, c2x2 equals 0 if x2t applied by the differential operator equals 0. So if we sum these two, then operator c1x1, c2x2 equals 0. Thus, this is also a solution. And c1 and c2 are arbitrary constants. That is called the superposition principle. It's also important to note that the differential equation determines any higher order derivative in terms of function value and first order derivative. Because if you substitute, if the equation itself gives ax double prime plus bx prime cx equals 0, then you can solve x double prime equals to minus bx prime minus cx over a. Always, second order derivative is always expressed in terms of function and it's the first order derivative. In addition, we take another derivative, then the third order derivative is expressed in terms of both second order and first order derivative. And the second order derivative is also can further be expressed in terms of x and x prime. Eventually, any higher order derivative of x is expressed in terms of x and x prime only. That's the reason why we have two independent undetermined parameters that completely determines a final result, final answer for your question. If we make a Taylor series expansion, then Taylor series expansion, we have f of x0 plus alpha equals the sum k runs from 0 to infinity, k factorial, f k the derivative at x equals 0, and alpha to the k. We need to know the derivatives, differential coefficient to any order. However, because this function satisfies this differential equation, the independent parameters for the whole derivatives at x equals x0 are only 2. So there are only 2 independent parameters to determine the complete solution for this linear differential equation, second order linear differential equation. So once the 2 independent parameters are determined, one can determine the complete solution for xt, called the general solution. General solution covers every solution to this differential equation. To find the general solution, it is inevitable to find the basis functions consisting of linearly independent solutions. The number of independent solutions must be 2 for the second order linear differential equation because the number of independent parameters is 2. Wronskian is a very nice tool to determine any given 2 functions are linearly independent for those functions that satisfy the second order linear differential equation. As I already told you, the solution to the second order differential equation have only 2 independent parameters, function and its derivative. So it is sufficient to compare the functional values and first order derivative for the for x1 and x2, the given functions. If the determinant is 0, then they are linearly dependent, and the determinant is non-zero, then the 2 solutions can be determined to be linearly independent. So once you find the linearly independent 2 solutions for the second order linear differential equation, your general solution is just a linear combination of 2 linearly independent solutions up to overall coefficient added up. Okay, we consider an equation of motion for a particle of mass m attached to a spring of spring constant k. X is the displacement from the equilibrium position. After rescaling the equation by mass of the particle, we find that x double dot plus omega squared x equals 0. Here, the angular frequency here, I have put omega, so let me put omega 0 here. Or we can, yes, this is, need to use omega 0. Okay, let me pass because we have already explained them previously. Exponential trial solution. A simple harmonic oscillator is a typical second order linear differential equation with respect to time, and L is a second order differential operator. Now, the second order differential operator for second order time derivative plus omega 0 squared, where omega 0 is square root k over m. Any linear differential equation can be solved easily by making the Fourier or Laplace transformation that extends the solution We know exponential x derivative is exponential x. Exponential ax, its derivative is a exponential x. So this form is always the same. So it is convenient to substitute the trial solution as an exponential form with some parameter, free parameter that is to be determined later. First order derivative of lambda t is lambda exponential lambda t, and nth order derivative of exponential lambda t is lambda to the n exponential lambda t. In this manner, if we substitute this exponential function as a trial solution for this second order differential equation with the operator for the simple harmonic oscillator, we find that the second order time derivative gives lambda squared, and constant term is omega squared, and they are factored out, and we have common factor exponential lambda t. Because if this is a solution, the right side must vanish. We know for any value of argument for the exponential function never becomes zero. So the only possibility of satisfying this equation is over coefficient that is factored out, the lambda squared plus omega squared equals zero. The solution to this equation is a plus minus I omega 0, and we have exponential e to the I omega 0 t and exponential my omega 0 t. These two solutions are obtained. We can compute the Wronskian of these two functions, and it is as long as omega 0 is not 0, they are linearly independent. Because we have found the two linearly independent solutions, we have already seen for the second order linear differential equation, there must be only two linearly independent solutions. But we have found a complete set of linearly independent solutions that are exponential I omega 0 t and exponential minus I omega 0 t. Hence, the linear combination of these two functions with arbitrary coefficients, the general solution is completely obtained. We know e to the I theta is cosine theta plus I sine theta, and e to the minus I theta equals cosine theta minus I sine theta. Hence, this expansion can be replaced with cosine and sine. In addition, cosine and sine can be combined into sine omega t minus delta or cosine omega 0 t minus delta with some amplitude. So there are many representations, but for your convenience, you can choose any one of these representations for the general solution for the simple harmonic oscillator. Combining the two terms into a single piece is expressed in the problem 8. These two, we have cosine kept the same. We multiply square root 1, square root c1, c2, and we have c1, c2 square over c1, c2, something, equal to c1 square, c2 square. Square and sum of these two must be 1. Therefore, they can be expressed as either cosine or sine. So let us choose to say it is cosine phi. This one is minus sine phi. Minus sine phi. Then cosine, cosine, sine, sine. So this simplification is possible. All right. Energy in simple harmonic motion. The simple harmonic oscillator satisfies this equation by making use of chain rule. Derivative of a squared is 2a derivative of a. Time derivative is expressed in terms of a dot, so 2a times a dot is the time derivative of a squared. In a similar manner, time derivative a dot squared can be expressed as 2 times a dot and a double dot. All right. So we multiply x dot here. Then what we obtain is x dot, x double dot, x dot, x double dot, x dot, omega 0 squared. Rearranging this equation, we find by making use of this one. Hence, this is 1/2 x squared time derivative is x dot. In a similar manner, time derivative 1/2 x dot squared equals x dot, x double dot. So sum of these two, time derivative of 1/2 x squared plus x dot squared equals x dot plus x dot, x double dot. Sure, we had better multiply the omega 0 squared in here. Omega 0 squared in here. And we will find is x dot this is equation of motion, so this is 0. What does it mean? This, if we consider omega 0 is k over m, this expression is simply expressed as this. What is that? This is kinetic energy. And this is potential energy. So, sum of kinetic energy and potential energy. The total mechanical energy. Total mechanical energy is conserved in the simple harmonic oscillator. Thus, the equation of motion derives the conservation of mechanical energy in simple harmonic oscillator. Next, we consider non-homogeneous linear differential equation that has non-vanishing value on the right-hand side. In physics problem, non-homogeneous linear differential equation is related to driven system. There is a driven damped harmonic oscillator. So this is a driving force. L is a second order linear differential operator. What we consider is an equation of motion. They are all second order linear differential equation. If there is a solution that satisfies the differential equation, then we call it particular solution. Particular solution. The general solution for the differential equation is a particular solution, sum of particular solution and the other. And the other is the solution for Lx equals 0. That is homogeneous, corresponding homogeneous differential equation. So the homogeneous differential equation solution is always necessary to find the general solution for the non-homogeneous differential equation. The particular solution can be obtained by chance or by inspection, depending on your experience. And mostly they can be obtained trivially. But solution for the corresponding homogeneous differential equation is rather tricky for the first time. But if you are trained, it is straightforward to obtain the result. Let us add the damping force to find the most general form of the second order linear differential equation that appears in physics problem for the damped harmonic oscillator. First, F equals ma. Ma means m double dot x is sum of forces. First of all, spring force minus kx and minus bx dot, this one is a damping force. And in non-homogeneous case, plus some, for example, gravitational force, something like that. So in this way, we superpose the applied forces to find out the equation of motion of a system. In this problem, damping force and constant gravitational force is included, and spring force is omitted. So this is the case we consider. We can move this x dot to the left hand side, and we find that x double dot is acceleration, and it is a time derivative of velocity. And this is bv, bx dot equals bv. Therefore, the expression is simplified on the left, and the right side g. So this is simplified into a first order differential equation. Let us first find out the particular solution. Suppose just constant substitution. Constant. Substitute constant to this. Then the first contribution will disappear. Then constant must be g. So particular solution should be g mg over b. We have obtained the particular solution. Next, we need to obtain the general solution for the corresponding homogeneous differential equation. Homogeneous differential equation has the same form on the left side, and right side is 0. So this is a homogeneous. This homogeneous equation can be solved directly by integration. You know, dv over dt equals minus p over mv. So this separation of variable. Okay, this one can be integrated. This one is log. Finally, the answer is exponential. Alright. This integration can be done. We can obtain this in this way. However, we can also obtain the result by substituting this trial solution. This trial solution, as we already explained above. Exponential trial solution. Anyway, velocity is expressed in terms of the particular solution. This one is particular solution. And homogeneous equation solution. Sure, you have to multiply arbitrary constant that can be determined from your initial condition. The damped harmonic motion is to be considered next. There is a damping force, spring force, and damping force. Damping force is always opposite to the velocity. Velocity and minus BV, here B because the sign of B is positive, so damping force, F damp. Damping force is always opposite to the direction of motion. So power of damping force, power FV, F damp dot velocity, that is minus B V vector squared. So this is a negative definite. So damping force, energy loss. Damping force give rise to energy loss. Finally, equation of motion, F equals ma, so mx double dot equals this. This equation becomes mx double dot plus bx dot plus kx equals 0. We rescale this equation by dividing the equation by mass m. Then we have x double dot plus b over m x dot plus k over m x equals 0. We call this coefficient b is damping coefficient, but for simplicity we use gamma, and we already defined this one to be omega 0 squared, where omega 0 is the square root k over m is the characteristic frequency of the simple harmonic oscillator. Alright, so we want to solve this equation. This equation can be solved by substituting the exponential trial function. The second order time derivative will give rise to the lambda squared. First order time derivative will give rise to lambda, and your final answer can be obtained by solving this quadratic equation. The solution to this quadratic equation is given by lambda equals 1/2 minus gamma plus minus square root gamma square minus 4 omega 0 squared. You notice that this discriminant may be positive, may be equal, or may negative. If it is positive, we have lambdas are real. Two real solutions. And if discriminant means inside the square root. The high school you learned is a capital D. Okay, equals 0, and you have a single real, one real, so this is double root, and then if it is negative, it becomes two complex solutions. Okay, positive or equal means this gamma is greater than 2 omega 0. Gamma equals 2 omega 0 is double, so real, and 2 omega 0 is greater than gamma is complex. Actually, the solution is related to damping dominance, and this is called over-damped. This is for critically damped. And this is under-damped. Finally, under-damped case, we have two complex numbers. First factor gives the exponential decay of the amplitude, and this when 2 omega 0 is greater than gamma, this results in the oscillating behavior. And you notice this omega prime is actually, what's that? If we consider factor of 2 here, so this one is omega 0 square root yes. It is already written below. Omega prime is in here. This is omega prime. You know, omega prime is slightly smaller than omega original characteristic frequency. The amplitude is decaying. Hence, so under-damped motion oscillation is something like that. So exponential decay of the amplitude. And period period oscillation, and actually this is not a periodic motion because the amplitude decay is very small. As far as this time gap is concerned, this period can be treated like that. For overdamped motion, there's no I. There's no I. Overdamped motion, there's no way of oscillating behavior. It is a purely exponential. So the damping like that. Even though there is a spring, there's no way of oscillation. The friction is large enough. For example, your door hinge has a very strong frictional force, then door does not oscillate. Instead, when you open the door and when it returns to close the door, because of a large damping force, it slows down and does not oscillate. But if the frictional force decreases, this door can oscillate, but amplitude decreases. So that is underdamped motion. But if there is no oscillation, your answer will be overdamped motion without any oscillating factor. An additional solution is for the double root case that is called the critically damped motion. And critically damped motion is solved in various ways. Can be solved in various ways, but we just follow this calculation to find out how to find the linearly independent set of solutions for the critically damped motion. Okay. Next, we consider some complex number. Complex number is very convenient to solve the damped harmonic oscillator and many solutions for the second order differential equation. In the future, even after we've been completing the circuit analysis for RLC circuit, we study some diffractive pattern, interference pattern, relevant to the light wave interference. In that case, if we make use of complex numbers, especially the polar coordinate representation for the complex number that is called the phasor, our calculation will be greatly simplified. Thus, at the end of this class, we review some useful method of complex numbers. First of all, we define the complex number I. This pure imaginary number I is a root of -1, a root of solution for this one. Your solution for this one is x equals to plus -1. And what about solution for -1? You have the solution plus minus square root -1. So I have plus minus I. Hence, I squared must be -1 because this quadratic equation is x squared is -1. A complex number z is defined by a linear combination of 1 and I with the coefficient. real coefficients x and y. Okay? Addition of two complex numbers can be made separately for the real part and imaginary part. Here, this is real part and this is imaginary part. Product of two complex numbers can be done by making use of identity from the definition for I. So I squared minus 1. If you multiply two complex numbers, real x1, x2, imaginary I squared minus 1, so y1, y2, negative sign on it. And if I have a single I, the x1, y2 and y1, x2, the result is like that. As I already told you, real part of a complex number is x, imaginary part of a complex number is y. Complex conjugate is z star is defined by a complex number whose real part is the same as z, but whose imaginary part is opposite in sign. Modulus z, the absolute value of a complex number z, is defined by the square root of z times z star. We multiply z and z star is x plus iy, x minus iy. That means x squared minus iy squared, that is x squared plus y squared, and two real numbers squared sum, that is always non-negative. So square root of z star is always non-negative, and that is defined by the absolute value of z, or modulus. Argument theta of a complex number can be defined in such a way: a complex number x plus iy can be expressed as a polar coordinate. The radius r, that is the modulus z, and angle theta is just the polar angle with respect to the real axis, real z and imaginary part of z. Okay, so z can be expressed in terms of z absolute value cosine, I z absolute value sine, and we define e to the I theta to be cosine plus I sine theta. We can prove this by expanding this or finding out the boundary condition and the differential equation that is satisfied by this equation, this number, this function. For example, exponential 0 is always 1, and derivative, you can take the derivative of this. The cosine's derivative is minus sine, and sine's derivative of cosine. You find that you can factor I out, and you again find cosine theta plus I sine theta, that is exponential I theta. Thus, if you take the derivative with respect to theta, it is just I e to the I theta. That satisfies the basic rule for exponential function. So let's say now to find that this expression e to the I theta, cosine theta plus I sine theta, is exponential I theta. In the phasor calculation, it is very useful to find out the sum or the product of the complex numbers. If you make a product, then exponential, the argument of the exponential adds up. Hence, the product of two complex numbers brings in the magnitude, that is the product of the magnitudes, and the argument is the sum of the two arguments. In the driven damped harmonic oscillator, we can exponential z when z equals a complex number this is real part and imaginary part can be separated into two pieces. We can consider the driven damped harmonic oscillator by including driving force. Damped harmonic oscillator, we have already explained the result, and we rescale this equation by dividing this equation by the mass. Then we end up with the rescaled equation, non-homogeneous equation. This non-homogeneous equation solution can be found by substituting the trial solution depending on the sinusoidal function. However, it is more convenient to make use of complex numbers. We note that these coefficients are all real. That's quite important. And what about introducing another solution y that has different part? However, this is cosine and this is sine. Aha, you have noticed that cosine theta plus I sine theta equals e to the I theta. We want to make use of this. That means if I multiply I to the lower equation and add them up, then what I obtain is a z double prime plus gamma z plus omega 0 square z equals a0 e to the I omega t, where z equals x plus iy. Although we are asked to find the solution for x, we do not have to solve the complicated problem. Instead, we solve a very simple problem relative to this asymmetry. The different cosine and sine are different. However, we can solve this equation in a very simple way and project out the real part to find out the solution for x. But sometimes we are asked to find the solution for the right hand side sine omega t. Then you can just take the imaginary part instead of the real part of this equation. Thus, in a similar manner, your answer will be sum of the particular solution and the general solution for the corresponding homogeneous equation. And particular solution can be obtained by substituting this same functional form except for the amplitude. As a result, we have all the same solutions for the homogeneous part, and what we are interested in determining the particular solution. The particular solution can be obtained by substituting the trial solution on determined amplitude and substitute the same functional form as the right hand side. Then you will find this exponential factor disappears, and this is a function. This is the equation for the amplitude. But you will find there is a complex number that appears. The phase vector, the phase constant, can be determined if we make use of this complex number analysis. The phase constant can be determined in such a way by reorganizing the calculation. These are the same thing, but this is the complex conjugate to make realize the complex denominator. Then the numerator has an opposite sign in front of the opposite sign because it is a complex conjugate. You mean we have complex number 1 over z, then it can always be expressed as z star and z star, and z star is absolute value squared and z star. This one is a star, so this negative sign in comparison is always positive sign in the denominator is understood as this one. And denominator does not have I anymore, so we say it is realized. It used to be a complex number, it became a real number, so it is realized. After realizing the denominator, it is easy to determine the phase constant using this numerator vector, that is this. Finally, combining this result, this time-dependent vector, your particular solution is finally determined as this. Because our right-hand side question was cosine omega t, we just take the real part of this complex solution to determine the particular solution. If it were a sine omega t, then we could have taken the imaginary part. Okay. You can consider further about the resonance behavior when amplitude is maximized. That's it.